make a more generalized definition of an acid and base then in terms of this transferring of protons, because that's what leads to acidic and basic solution for transfer of protons. So Bronsted and Lowry came up with a more general definition of acids and bases. What they did was they classified the species, the ions or the molecules, instead of just the substance. Okay, the substance is just a collection of ions and molecules, or ions or molecules. But in the Bronsted-Lowry definition, what we call the acid and the base are the molecules themselves or the ions themselves. Okay? So according to the Bronsted-Lowry definition, an acid-base reaction is one that involves a transfer of a proton, transfer of H+, from one species to another. So any reaction that involves proton transfer is called an acid-base reaction. So this is a more generic definition of acids and bases. And so during a proton transfer reaction, the species that loses the proton, that's called your proton donor, that's your acid. Okay? So the acid is the proton donor. The species that accepts the proton, that gains a proton, or the proton acceptor, is your base. Okay? So this allows you to explain acidic and basic salt solutions as we showed earlier. Essentially, how does this explain it? The ions may react with water to form H+ or hydroxide. What did we say happened, for example, to an ammonium salt? One of these hydrogens can transfer. Okay, one of these protons can transfer as a proton. One of these hydrogens can transfer as a proton to a water molecule, giving you hydronium ion. And what did we say happened to a carbonate ion? A proton from a water molecule can hop onto this carbonate ion, leaving behind a hydroxide. Okay? So that's the Bronsted-Lowry definition. All right, so here's a quick check. For this reaction, the autoionization of water, this involves proton transfer, right? From one water molecule to another water molecule. So for the forward reaction, what's the acid and what's the base? According to the Bronsted-Lowry definition. So what happened here? Okay. Let's see, what happened here? A proton transfers from here to here, right? So what's the acid? The acid is where the proton came from. The donor, what's the donor? H2O. What's the acceptor? Also H2O. So the acid is H2O, the base is H2O. Okay? So correct answer is A. Alright? So that's what we mean by Bronsted. So in this particular case, we say that the acid and the base is the same molecule, right? The same type of molecule. Water, you'll notice, is capable of donating a proton. It's capable of accepting a proton. You call it an amphiprotic species. Okay? Amphi means like amphibian, can go either way, land or water. An amphitheater is what? You can see it from both sides, the stage, right? So amphiprotic would be a species that can either accept or donate a proton. It can either act as a Bronsted acid or a Bronsted base. For the reverse reaction, remember this reaction is reversible, in fact. So if you were going back and hydronium was to give back its proton, okay, give its proton to hydroxide to give you two water molecules, what's the acid for the reverse reaction and what's the base? This time the donor is hydronium and the acceptor is hydroxide. Okay, so the acid is hydronium and the base is hydroxide. Okay, so in an acid-base reaction, okay, there's when you transfer a proton from one species to another, the proton can transfer back, right? And so the reverse reaction is also a proton transfer reaction. So what did we notice? This was an acid, this was the base, right? And then what happened? This is the acid, and that's the base, right? For the reverse reaction, let me color code it. So for the reverse reaction, this is the acid, and that's the base. So where did this H3O plus come from? From a water that gained a proton, right? It came from this, right? So this H2O and H3O plus, we say, is a conjugate acid-base pair. Water is the base, its conjugate acid is H3O plus. Where did this hydroxide come from? From the water that lost the proton, right? So this thing right here, this acid and base right here, H2O and OH minus, water and hydroxide, is also a conjugate acid-base pair. So that's what conjugate acid-base means. So what's the difference between a conjugate acid and a conjugate base in the pair? The acid has one more proton compared to the base, right? This acid has one more proton compared to its conjugate base. That's the difference, okay? Let's try this one. Cyanide plus water gives you HCN plus hydroxide. The base for the forward reaction and the base for the reverse reaction. Okay? So, what's the base? The acceptor. What happened here? This H2O lost a proton, right? It transferred over to the cyanide to give you HCN. So what's the base for the forward reaction? The cyanide. Okay, and that's the acceptor, right? What's the base for the reverse reaction? If the reaction were to go in reverse, what would have happened? How do you get back your cyanide? This H plus has to transfer over to give you water, leaving behind a cyanide. So for the reverse reaction, what's your base? It would be your hydroxide. Okay? So correct answer is A.